Every year, the world produces over 200 million kilometers of cable, enough to wrap around the Earth 5,000 times. But few people know that the heart of every electric car is not just the battery, but also a cable that can withstand voltage, temperature, pressure, bends, and vibration. How are these high-tech wires created, capable of working in conditions where even metal seems alive? How do scrap, dust, and molten aluminum turn into the arteries of Tesla, Rivian, and Lucid? In this video, the whole truth about the most engineered wire of the 21st century. Every cable for an electric car is a strategic choice. It must be flexible but not brittle, conductive but not vulnerable, lightweight but capable of withstanding hundreds of amps and thousands of hours of voltage. And when engineers sit down at the drawing board, they are like alchemists of the future, mixing formulas of elements in their heads, searching for the perfect balance. Copper is the good old classic. It conducts electricity better than anything else, and it's its heart that beats in most cables. But the weight? Oh, that weight! An electric car needs to be as light as a cat, so aluminum often steps in as a substitute. It's cheaper and lighter, though not as conductive. But in the right alloy, it's already a weapon of the electric age. And around it, insulation. These are highly engineered polymers that can withstand heat, cold, chemicals, vibration, dust, and even a small lightning strike under the hood. They lack the shine or weight of metals, but without them, everything would turn into a sparkling inferno. Some cables have shielding, a thin armor of copper braiding or aluminum foil. It protects signals from interference, because in an electric car, not only kilowatts are important, but every millivolt of data too. Aluminum isn't born shiny. First, it's rough ingots, each weighing over 1,000 pounds. They arrive at the factory like aliens from their ore world, extracted from bauxite, purified, remelted, and finally formed into rectangular blocks resembling metal sarcophagi. These ingots arrive in large trailers, carrying tens of thousands of pounds of the future. By appearance, they are just shiny silver blocks, neatly stacked on steel pallets. But just get closer, and you'll feel it. A warmth of energy emanates from them, encapsulated in atoms. Sometimes, instead of ingots, the factory receives aluminum coils. This is already processed aluminum wire, wound into coils 3 or 4 feet in diameter, each weighing about 500 pounds. They shine like snake coils and glisten in the light, as if they just came out of a cybernetic beehive. Separate batches are supplied as aluminum scrap, meaning leftovers from other productions, cuttings, shavings, fragments of frames. They are sorted, cleaned, remelted, because in this future, not a single crumb of metal goes to waste. As soon as aluminum enters the factory gates, it is identified, tested, and marked. In the first stage, technicians inspect the ingots or coils, checking for cracks, corrosion, impurities on the surface. It's like a quick checkup, by eye, by hand, with a scanner. If rust, oxidation spots, or transport damage are noticed, the metal is either sent for remelting or rejected. Next, chemical expertise. A piece of each ingot is taken and checked on a spectrometer. This device shoots the metal with a laser, captures the reflected waves, and shows how much aluminum, iron, silicon, copper, magnesium, and other elements it contains. The goal is to make sure it's the right grade. After passing the tests, the ingots are marked with a batch identification number, alloy grade, date and place of melting, and sometimes a QR code that leads to a full technical passport. It's like a birth certificate that will travel with the metal until the moment it becomes wire and ends up inside a Tesla, Rivian, or Lucid. When the ingots have passed inspection and received their quality mark, they are loaded into giant electric or gas furnaces. The temperature inside, over 1,220 degrees Fahrenheit, is exactly what's needed to turn aluminum into liquid silver. No alchemy. We're talking about molten metal. The damper opens, and massive cranes carefully lower the ingots into the red-hot interior. The metal slowly melts, releasing a gray vapor and a strange smell, a chemical mixture resembling heated foil and ozone. Nearby, operators in heat-resistant suits looking like astronauts carefully monitor the furnace indicators: temperature, impurity level, viscosity. No mistakes are allowed here, as the cable for an electric car must withstand thousands of miles and hundreds of charges. A slag layer appears on the surface of the molten metal: impurities, oxides, residues of alkaline metals. It is removed manually or by automatic systems to leave only a clean, homogeneous mass. Sometimes, modifiers or alloying elements are added to give the metal the desired properties: more conductivity, strength, flexibility. Molten aluminum is poured into casting molds, usually round blanks 4 to 6 inches in diameter and up to 10 feet long. These are the future rods from which cables will be drawn. The process is called casting billets. Cooling is controlled in stages to avoid cracks. All this is accompanied by hissing steam, the roar of pumps, and a rhythmic thud, the heartbeat of the cable factory. So what is drawing? It's a process where aluminum rods are pulled through a series of increasingly narrow holes. With each pass, the metal becomes thinner, longer, and stronger. Like a piece of dough being rolled out into noodles, only instead of dough, it's hot aluminum, and instead of a rolling pin, hydraulic machines weighing tens of tons. Before drawing, the blank is heated to an optimal temperature, no more than 650 degrees Fahrenheit, so it becomes plastic but doesn't melt. Then it's fed into a drawing machine, where the magical transformation begins. Each pass through the die reduces the wire's diameter by a few percent. It's like passing through increasingly tight doors, forcing the material to stretch. After a dozen such passes, a thick rod half an inch in diameter becomes a slender strand 0.1 inch thick or even less. During drawing, the wire heats up from friction, so it's constantly cooled with water or special lubricants. Without this, it would overheat, lose its shape, or even break. Lubrication also reduces wear on the tools, dies made of carbide or diamond. Some machines can draw wire at speeds over 2,000 feet per minute. It's like someone pulling a spider web from a ball of lightning. Engineers carefully monitor the tension, temperature, shape, and shine of the wire, because even the smallest crack or geometry violation is a future short circuit in a $60,000 car. When the drawing is complete, the cable thread already looks like a shining string for a future electro-magical harp. It's long, thin, conductive, but still stubborn. To be able to wrap around batteries, penetrate narrow body channels, and withstand hundreds of thousands of bends in the motion of an electric car, it needs to be annealed. The wire slowly passes through furnaces without an open flame, or through an induction field that heats it from the inside. The temperature, around 600 degrees Fahrenheit. This is the point where the metal doesn't melt, but changes its character. The atoms, which until now held onto their nodes in a stressed crystal lattice, finally relax. Like soldiers after a battle, like a string that has sounded at its maximum, and finally fallen silent. The metal structure becomes more uniform, the grains larger, and the wire itself flexible, elastic, calm. The surface of the wire after heat treatment is darkish, with scale or signs of oxidation. It is cleaned off with abrasive brushes or in chemical baths. Aluminum must shine, like a star before a rocket launch. The cleaner the surface, the better the insulation will adhere. Next, insulation. An ultra-thin layer of material is applied to the wire, separating it from everything except the current. This can be polyethylene, Teflon, silicone, or enamel, depending on the cable's intended purpose. The material is applied in liquid form, often in heated baths or through nozzles that cover the wire with a uniform flow. The application temperature, over 400 degrees Fahrenheit. As soon as it's applied, it's immediately baked. The insulation doesn't dry, it polymerizes. It's like creating a skin around the nervous system. It must be perfectly even, dense, without microcracks. Otherwise, the wire won't pass the test. Next, the wire passes through detectors that check it for breakdown, coating thickness, and electrical resistance. At least once every 1,000 feet, samples are taken manually and checked under a microscope. Everything is recorded because this wire will later work in high-voltage systems. The finished wire is cooled, lubricated to reduce friction, and then carefully wound onto drums or spools, sometimes up to 5,000 feet long. This is no longer just metal, it's the nerve of an electric car, ready to hit the road. Did you know that the machines powering global industry, transportation, and our electrical grids consume energy equivalent to building thousands of the Great Pyramids of Giza every single day? This hidden power isn't just about raw force. It's delivered by some of the most massive and awe-inspiring engines ever conceived. From the dawn of the industrial age to today's modern world, engineers have chased the dream of bigger, stronger, more efficient powerhouses. Get ready to take a journey through history and dive into the incredible scale and engineering genius behind the world's most powerful and giant engines. Our journey begins in the age of steam, a time when raw pressure was king. Picture the late 18th and 19th centuries. The engines that drove the Industrial Revolution weren't small. Early steam engines were clunky, but they quickly grew into colossal machines. Think of the beam engines, towering structures in factories and mines, with massive beams rocking back and forth, driving pumps and machinery with the power of boiling water. These were mechanical giants, their sheer physical size necessary to contain the immense forces of steam pressure. As steam technology evolved, so did the engine's power and scale. Reciprocating steam engines became the heartbeat of global shipping. Imagine the engine room of a massive early 20th century ocean liner. You'd see multi-cylinder engines with pistons the size of trash cans, connecting rods like tree trunks, and crankshafts so large they needed multiple men just to inspect them. These engines were colossal, spanning multiple decks, their rhythmic pounding driving propellers powerful enough to push thousands of tons across vast oceans. They were engineering marvels of immense moving parts, powered by the simple expansion of steam. While steam dominated for a long time, the early 20th century saw the rise of a new kind of giant, the diesel engine. Unlike external combustion steam engines, diesels burn fuel directly inside the cylinder. This was a game changer for efficiency and power density. Early large diesels quickly found their way into ships and power generation. Imagine a large, slow-speed marine diesel engine built for a cargo ship. These engines are absolutely colossal, often standing as tall as a multi-story building and stretching the length of a gymnasium. Modern marine diesel engines, like some built by Wärtsilä or MAN, are among the largest machines on Earth. The biggest ones have multiple cylinders, each with a bore, diameter. Wider than a grown man is tall. Their crankshafts are multi-piece monsters, weighing hundreds of tons. These engines produce over 100,000 horsepower, enough to move supertankers and container ships carrying 20,000 containers. The sheer scale of these components, pistons, connecting rods, crankshafts, cylinder blocks, is mind-blowing, a testament to achieving immense power and torque from internal combustion. As technology advanced further, especially in the mid-20th century, the gas turbine emerged as another powerhouse. Unlike diesels or steam engines that use pistons, gas turbines burn fuel to create hot gas that spins a turbine wheel, similar to a jet engine. While aircraft engines are built for power to weight, industrial and power generation gas turbines are built for sheer output. Imagine a power plant gas turbine the size of a bus or even a small house. Modern industrial gas turbines, like those in GE's H-Class, are engineering marvels generating hundreds of thousands of kilowatts, enough electricity for hundreds of thousands of homes from a single unit. They involve incredibly complex internal components, spinning at thousands of revolutions per minute in temperatures hotter than molten lava. Their power output, efficiency, and relative compactness compared to older technologies make them the giants of modern electrical generation. Some large ships, including cruise liners, also use gas turbines for their combination of power and smoother operation. Comparing these generations of giants is fascinating. Steam engines were the pioneers, relying on brute pressure and massive physical structures. Diesel engines brought efficiency and incredible low-end torque, dominating heavy transport. Gas turbines delivered immense power density and high-speed rotation, becoming the backbone of modern power grids and high-speed applications. Each technology pushed the boundaries of materials, science, and engineering to harness energy on an ever-increasing scale. These engines, whether the visible, rhythmic giants of the steam age or the humming complex powerhouses of today, are the unseen heart of the modern world. They drive global trade across oceans, power the trains that move goods and people, generate the electricity that lights our cities and runs our factories, and fuel the massive pumps and machinery of heavy industry. They are a testament to humanity's relentless drive to build bigger, stronger, and more powerful machines. So, the next time you see a massive cargo ship, a powerful train, or simply flip a light switch, take a moment to remember the incredible journey through history and the engineering genius behind the world's most powerful and giant engines. From towering steam engines and colossal marine diesels to blazing hot gas turbines, they are the hidden giants that built our modern world. What era or type of giant engine fascinates you the most? Let us know in the comments. Every second globally, over 3 billion gigabytes of data are transmitted. But did you know that all this happens thanks to a thread thinner than a human hair? And that this thread starts with ordinary sand. Not beach sand, but perfectly pure quartz, where there's only one impurity per million parts. To create fiber optic cable that transmits light at a speed exceeding 300,000 kilometers per second, you have to go through a journey involving chemical vapors, sterile laboratories, a 2,500-degree furnace, and lasers that monitor every microcrack. This process looks more like manufacturing a spaceship than a cable, but it is the foundation of the internet you are using right now. To create a thread capable of transmitting light at a speed exceeding 186,000 miles per second, you have to start with sand. But not just any sand. Only special, extremely pure quartz sand, where the main substance is silicon dioxide. For fiber optic production, Sand with a silica content of over 99.9% is used, meaning in 1 million parts, there's only 1 part of impurities. Imagine this. In every pound of raw material, no more than a few millionths of an ounce of impurities. And this is critical, because even 1 billionth of an inch of foreign metal or organic matter can cause light scattering or absorption in the fiber optic cable. And then the signal, which was supposed to travel 60 miles without amplification, simply disappears. Raw material for fiber optic cable isn't just washed or filtered, it's purified at the molecular level. Manufacturers often use vapor phase chemistry. Quartz sand is converted into gaseous silicon tetrachloride, which is then distilled, filtered, and deposited as pure vapor. And only then is it converted back into glass. Add to this strict control of temperature, humidity, air currents in clean rooms, and you'll get an idea of how far this is from an ordinary sandy beach. Production laboratories look more like National Aeronautics and Space Administration sterile zones than a glass workshop. And all for the sake of ensuring there's not a single defect in every yard of the future fiber. Because when you're transmitting light over thousands of miles, even one microscratch can cost you signal quality. A large transparent glass cylinder that will later be melted and drawn into a very thin thread. This is the fiber optic preform. This huge glass rod is made using a method called vapor deposition. In a large furnace, air is mixed with very pure gases. These are different substances that turn into vapor when heated. These vapors hit the inner surface of a transparent tube, which is heated very intensely. When the vapors touch the hot wall of the tube, they deposit and turn into tiny droplets of glass, like dew collecting on leaves in the morning. Gradually, these droplets collect, layer by layer, until a thick layer of glass forms inside the tube. Then this tube is heated even more intensely, and it collapses into a dense solid rod. And this is our preform. The preform is placed in a special furnace that heats up very intensely. The temperature inside it reaches approximately 4,700 degrees Fahrenheit. This temperature is so high that the glass becomes soft and starts to melt, like caramel on a stove. When the end of the preform melts, a drop of molten glass begins to drip from it. This drop is very carefully drawn downwards, and a thin thread is formed from it. This thread, the optical fiber, is drawn at a speed of approximately 1,000 feet per minute. Imagine that. It's faster than a cyclist moving through the city. It's important for the thread to be of uniform thickness throughout its length. The thickness of an optical fiber is usually around 125 microns, or approximately 0.005 inches. That's very, very thin. For comparison, the average human hair is about 100 microns thick or less. To keep this diameter under control, special instruments are used during the process. They look at the thread in real time and measure its thickness. If the thread starts to become thicker or thinner, the system automatically changes the drawing speed or the furnace temperature to correct it. After the optical fiber has been drawn from the preform and has become a thin, transparent thread, it needs to be protected. The fiber is very thin and fragile. If left unprotected, it can easily break. Cracks will appear, or dirt will get on it. Therefore, immediately after drawing, the fiber is coated with a special protective layer. A thin thread is pulled from the furnace. After the furnace, the thread immediately goes into a coating machine. This is a special device that clothes the thread in a plastic sheath. The optical fiber enters a special part of the machine called the coating head. It's like a small tube or nozzle, inside which there's molten protective material. As the fiber passes through this tube, a layer of liquid polymer is evenly applied to it. The polymer has very low viscosity, so that the coating is thin and even, but dense enough to protect the fiber. This coating layer usually consists of two parts. The primary coating is a very soft, elastic layer that dampens mechanical shocks and allows the fiber to bend. The secondary coating is harder and more rigid, protecting against external influences, dust, and scratches. These two layers are applied sequentially, one after the other, to provide reliable protection. After applying the liquid coating, the coated fiber passes through special forming rollers. They regulate the thickness and evenness of the layer, pressing the coating uniformly along the entire length of the fiber. These rollers are very precisely calibrated so that the layer is not too thick or thin. After the polymer has been applied and shaped, the fiber passes through a zone of ultraviolet light. Here, the polymer instantly hardens under the influence of ultraviolet lamps. This is a process called polymerization. Anyone who gets their nails done knows how this happens. Ultraviolet lamps emit light of a specific wavelength that activates chemical reactions in the polymer. Thanks to this, the coating quickly becomes solid, while retaining its elasticity and ability to protect the fiber. This is a very fast process. The coating solidifies in fractions of a second, literally. This method does not heat the fiber, so it doesn't damage it. This provides very strong and durable protection. The entire machine is equipped with sensors and control systems. They constantly measure the coating thickness, fiber feed speed, and uniformity of application. If the coating layer is too thin or there are defects, the system either stops the process or adjusts the parameters to avoid defects. At the end of all this technological magic, a spooling module, rotating with a hum resembling the sound of a jet engine, only in miniature. The fiber, like transparent silk, lies down smoothly and precisely, coil after coil. It shimmers in the light of the lamps, reflecting cold blue and white hues. The spool moves smoothly, to the left, then to the right, with millimeter precision, as if an artist is painting pictures with movement. One wrong angle, and everything will go haywire. So the system automatically adjusts the rotation speed and fiber tension with surgical precision. Around are sensors, lasers, cameras. They carefully ensure that the fiber lies flat, doesn't twist, and doesn't create tension. With every minute, more and more layers appear on the spool. Imagine, in a few hours, there are already several feet of thin, almost invisible fiber there. And all this, without a single break, without a single scratch. Because even a micro crack, and the light signal will get messed up, like a radio wave in a storm. Before cable assembly begins, the fiber from the spool is carefully wound onto a production line. Since one cable usually contains several fibers, individual threads are combined into ribbons or modules. For ribbons, the fibers are arranged parallel in a single plane, for example, 12 pieces, and glued together with a special resin. This makes them easier to work with during connection. For bundles, the fibers are twisted into a spiral strand and placed in a plastic tube. These ribbons or bundles are then placed into buffer tubes, thin, flexible plastic channels that provide space for the fiber's slight movements. This is important because when the cable's temperature changes or it's bent, the fiber slightly expands or contracts, and the buffer tube helps prevent it from being damaged. A gel that repels water and absorbs vibrations can also be added inside these tubes. Around the buffer tubes, strengthening elements are added. Fiberglass or Kevlar, very strong threads that protect the cable from stretching. Metal wire, for additional mechanical strength or grounding. A central strength member, a rigid element in the center that maintains the cable's shape. These reinforcements are needed so the cable can withstand tension, impacts, bending, and remain intact for decades. All of this is wrapped in an outer jacket. This is a dense plastic or polyethylene pipe resistant to ultraviolet light, moisture, rodents, temperature fluctuations. The cable is tested. The bandwidth of each fiber is checked, as is its bending strength and resistance to moisture. Then it's wound onto large drums, marked, and technical documents are added, and it's ready for transportation and installation. Did you know that over 100 million AK-47 pattern rifles have been produced worldwide since its invention? That's an absolutely staggering number, more than all the service rifles produced by almost every other country combined. This iconic weapon, recognized globally for its ruggedness and reliability, might seem incredibly simple on the outside. But producing these millions of units requires a massive, complex industrial process involving extreme forces, surprising precision, and manufacturing secrets perfected over decades. Get ready to go behind the curtain and see exactly how an AK-47 is manufactured on a colossal industrial scale. The story of the AK-47's manufacture really begins with its design philosophy. Mikhail Kalashnikov intended it to be simple, easy to use, reliable in the worst conditions, and crucially, easy and cheap to manufacture in vast numbers. This design genius meant engineers had to figure out how to make complex parts ruggedly and quickly. The key was often using methods that didn't require extreme precision machining on every single component, focusing tight tolerances only where absolutely necessary for function. This is a core secret behind its mass production success. One of the most visually impressive and important manufacturing processes for the AK-47 is IAE's stamping. Unlike many other rifles that use heavier, milled receivers, the AK-47 often uses a receiver made from sheet metal. Picture huge rolls of steel sheet being fed into massive, powerful presses. These presses stamp out the receiver's shape in stages, bending, forming, and punching the metal with tons of force. This high-speed stamping process is incredibly efficient, churning out receivers faster and cheaper than almost any other method. It's a core reason millions could be made. While the receiver is often stamped, many critical components that face extreme stress and heat, like the barrel, the bolt carrier, and the bolt itself, are made by forging. This involves heating steel billets, solid blocks of high-strength steel, to incredible temperatures until they're red-hot and malleable. Then, giant forging presses or hammers pound or squeeze these glowing pieces into complex shapes. The force involved is immense, thousands of tons, reshaping the metal's internal grain structure to make the part incredibly strong and durable. This is where raw power meets shaping, creating components tough enough to withstand the explosive forces of firing. Even though simplicity was key, certain areas of the AK-47 require remarkable machining precision for reliable function. The bolt, which locks into the receiver, and the chamber end of the barrel, where the cartridge sits, must meet tight tolerances. These parts are finished on computer numerical control machines that use hardened cutting tools to shape the tough steel with incredible accuracy. While not every surface needs mirror-like precision, the critical interfaces that ensure safe and reliable firing are machined to exact specifications, often measured in thousandths of an inch. Bringing all these parts together involves other vital metalworking processes. Welding is used to join stamped receiver components and attach parts like the gas block to the barrel. Industrial welding robots, or skilled human welders, create strong, reliable joints. Heat treatment is also critical. Components like the bolt and bolt carrier undergo processes like hardening and tempering, heating and cooling cycles that change the steel's properties, making them incredibly resistant to wear and impact, vital for the rifle's legendary durability in harsh conditions. Once all the metal components are fabricated and treated, they often go through finishing. This includes processes like parkerizing, bluing, or applying polymer coatings. These aren't just for looks. They're crucial for protecting the metal from corrosion, especially important for a rifle designed to operate in wet, muddy, or humid environments. Furniture, the stock, handguard, and pistol grip, is often made on separate lines from wood or polymer, and then added to the metal assembly. The final stage is Koblau assembly. While many steps are automated, putting together the hundreds of components of an AK-47 often still involves significant human skill on assembly lines. Workers fit parts together, install springs, pins, and levers, turning a pile of components into a functional rifle. Each rifle is inspected visually and functionally as it comes off the line. The true test of an AK-47's manufacturing is its legendary reliability, and this is verified through rigorous quality control and testing. Rifles are subjected to dimensional checks and material tests. Crucially, they undergo proof testing, firing rounds with an intentionally heavier charge than standard to ensure the weapon can safely withstand extreme pressure. Some are even subjected to brutal environmental tests, dunked in mud, buried in sand, submerged in water, and then expected to fire immediately. This extreme testing validates the ruggedness built into the manufacturing process. Producing millions of AK-47s requires vast factory complexes, intricate logistics, and a highly skilled workforce. It's a fascinating intersection of design philosophy, focused on simplicity, and industrial processes capable of achieving rugged reliability on an unprecedented scale. While the rifle itself is often seen as a symbol of conflict, its manufacturing process is undeniably a powerful example of mass production engineering and durability-focused fabrication. So, the next time you see an image of that instantly recognizable silhouette, remember the unseen journey it took. From raw steel and wood, through giant stamping presses, powerful forging hammers, precise machining centers, intense heat treatments, and rigorous testing, it's a product of a massive, impressive industrial process. It's a fascinating look into the power and precision that builds one of the world's most widespread tools. What part of manufacturing an AK-47 surprised you the most? Let us know in the comments. Did you know that each year the world faces the challenge of decommissioning millions of old electrical transformers? These metal giants, often found quietly powering our neighborhoods, can hide an incredibly dangerous secret. Many older units are filled with highly toxic chemicals, like deadly PCBs. A single misplaced cut or accidental spill could cause severe, long-lasting environmental damage across vast areas. Taking down these hazardous units isn't a typical scrapyard job. It requires a specialized, highly precise, and incredibly dangerous industrial process happening behind closed doors. Get ready to see the intense operation to safely dismantle these toxic time bombs. So, why exactly are these old transformers so dangerous? For decades, many relied on a coolant liquid called ascarel, which contains polychlorinated biphenyls, or PCBs. These chemicals are terrifyingly persistent in the environment. They don't break down easily, and they are highly toxic to humans and wildlife. Even a small leak from a neglected unit can contaminate soil and water for generations. Modern transformers use safer, non-toxic oils, but the legacy of PCBs in older units means they cannot simply be scrapped like regular metal waste. They demand specialized, heavily regulated facilities designed specifically to handle these hazardous materials with extreme care and containment. The intense process begins when old transformers, often behemoths weighing thousands or even tens of thousands of pounds, arrive at these specialized decommissioning plants. Picture massive yards filled with these silent, potentially hazardous giants, waiting to be processed on a dedicated industrial line. The absolute first step isn't dismantling or cutting. It's meticulous documentation and assessment. Each arriving unit is rigorously inspected, its history and potential contents checked to determine if it likely contains PCBs or other hazardous materials. They are categorized based on size, type, and estimated contamination level. This initial sorting on an industrial scale requires heavy-duty lifting equipment, massive cranes and powerful forklifts, just to move these incredibly heavy pieces of electrical history into position for the next stage. Once identified, categorized, and positioned, the transformers move onto the dedicated high-containment processing lines. The absolute priority here is total containment and zero exposure. Every single step is designed with redundant layers of safety to prevent any spills or contact with the toxic materials inside. Workers operating on these lines are encased head to toe in specialized protective gear. Full chemical suits, filtered respirators, multi-layered gloves. The air quality within the facility is under constant real-time monitoring. These are not standard factory conditions. They are hazardous material handling zones requiring maximum vigilance. The first critical task on this line is to meticulously drain the internal coolant oil. This oil, especially if it contains PCBs, is the most dangerous component, the liquid heart of the toxic secret. Draining the hazardous oil is a highly precise, high-containment operation, executed with surgical care. Transformers are carefully positioned over multi-layered sealed collection systems, often including large secondary containment basins designed to catch any potential leaks or spills, no matter how small. Workers use specialized pumps, leak-proof fittings, and designated tools to access drain valves and carefully remove every single drop of the hazardous oil directly into secure, heavy-duty, properly labeled tanks. This cannot be rushed. It's a slow, deliberate process. Think of it like disarming a complex device. Every connection, every hose is checked and rechecked multiple times. This step is the most crucial for protecting the environment from widespread contamination and ensuring the immediate safety of the workers directly interacting with the highly toxic liquid hidden within the steel shell. After every drop of oil is confirmed, safely drained, and contained, the transformer must be absolutely de-energized and rigorously verified as safe from any residual electrical voltage. Even units that have been disconnected for years can potentially hold a dangerous charge. Highly trained technicians follow strict, multi-step lockout, tagout, and grounding procedures, physically isolating the unit and discharging any potential buildup to ensure no electrical hazard remains before any physical dismantling tools come anywhere near the unit. Safety protocols here are layered and redundant, because any mistake made at this stage carries the risk of severe injury or worse. With all immediate electrical and chemical hazards neutralized, the physical dismantling begins. The process of breaking down the thick steel shell to access the valuable materials and internal components. This is heavy-duty, industrial demolition work requiring powerful tools. Workers use intense plasma cutters that slice through thick steel casings with incredible heat, powerful hydraulic shears that crunch through metal like paper, and heavy-duty saws. The internal components, massive, heavy copper windings, dense steel cores, and various insulation materials, are often incredibly weighty and must be carefully lifted out section by section using overhead cranes and specialized rigging. Imagine cutting open a giant, multi-layered steel safe filled with tangled, incredibly dense, and heavy metal structures. It's a loud, sparks-flying process, but it's executed with engineering precision to efficiently separate the different material streams. As the transformer is broken down piece by piece on the dismantling line, the various resulting materials are carefully sorted and separated onto different processing conveyors and areas. Valuable metals like the pure copper windings are isolated into their own stream and sent for high-grade recycling. Steel casings, cores, and other structural steel components are separated for scrap metal recycling. Aluminum parts are directed to their specific recycling stream. But the key challenge, the hazardous legacy, lies with the contaminated materials. Any solid components that came into direct contact with the toxic PCB oil, internal insulation paper, wooden bracing blocks, contaminated gaskets, even metal parts that absorb the chemical, are now classified as hazardous waste themselves. Handling and disposing of this hazardous solid waste requires extreme care and strict protocols. The safely drained PCB oil, the contaminated solid materials, and even the specialized protective gear worn by workers after handling these substances must be meticulously contained, documented, and transported for disposal according to stringent environmental regulations. This often involves complex logistics chains, moving the waste to highly specialized hazardous waste landfills designed to permanently isolate the toxins, or to permitted high-temperature incinerators, specifically designed and certified to safely destroy PCBs at extreme temperatures. It's a costly, complex, and highly regulated part of the process, a hidden necessary step ensuring those dangerous chemicals never re-enter the environment to cause harm. Despite the inherent dangers and complexities, dismantling old transformers represents a vital dual purpose. Primarily, it's about environmental protection and safely eliminating hazardous waste legacy units. But it's also a significant part of the circular economy and resource recovery. Valuable metals like pure copper, steel, and aluminum, weighing thousands of pounds in a single large unit, are recovered and reintroduced into the manufacturing supply chain. This reduces the need for environmentally impactful new mining operations. So, while the drive is safely neutralizing a threat, the process simultaneously recovers significant valuable resources, making it an essential, albeit dangerous, link in the critical lifecycle management of electrical infrastructure. These highly specialized decommissioning facilities are engineering marvels in their own right. They process hundreds, sometimes thousands of transformers each year, ranging from common small pole-mounted units you see everywhere to massive multi-ton substation giants. Each unit processed represents a potential environmental disaster safely averted and a source of valuable industrial materials recovered, all thanks to incredibly precise engineering processes, cutting-edge safety protocols, and the unwavering skill and courage of workers operating daily in a high-risk, high-containment environment. It's a critical industry that literally cleans up dangerous industrial history. So, the next time you see a transformer quietly working, or simply flip a light switch, take a moment to remember the unseen, dangerous, but absolutely essential industrial process happening far from view. The vital work of dismantling old, toxic giants, protecting our environment and communities from hidden chemical threats, and recovering valuable resources for the future. It's a fascinating, high-stakes look into a necessary industry few people ever see. What part of this hazardous but critical process surprised you the most? Let us know in the comments. Now, can you just picture this? Every single day on this planet, folks burn through over 9,900,000 barrels of oil. That's like what? 1 billion liters. Pretty wild to think about, right? But what is oil, really? How does this thick black goo actually get turned into the energy that powers our entire world? Today, we're gonna dive deep into the seriously fascinating world of oil production. We'll start with how it even forms over millions of years, then check out the incredible tech in modern wells that punch down tens of thousands of feet into the earth. We'll cover everything from those giant platforms way out in the middle of the ocean to the complex refining steps that take that raw material and turn it into clean fuel. Ready to find out the real story behind that black gold? Let's just jump in and see how natural gas really works. Folks are projecting that average oil production in the United States next year is going to hit right around 9,900,000 barrels per day. But honestly, do you even know what oil is, or where it even came from in the first place? I mean, everybody talks about oil this, oil that, oil spills, oil production. But nobody ever really tells you what it actually is. Well, stick with us, and we'll just break it down for you. The way oil forms is a seriously long-term project, taking millions of years. It kicks off with a bunch of organic stuff, like the leftovers from ancient plants and little critters, piling up on the bottom of old seas and lakes. Over time, these plant and animal remains get buried under layers of sedimentary rocks, things like clay and sand. Then, under a ton of pressure and heat, which gets way more intense the deeper you go, that organic material starts transforming into something called kerogen. It's kind of a solid, waxy material. If the temperature keeps cranking up, hitting somewhere between 140 and 302 degrees Fahrenheit, that kerogen breaks down using heat. And bam! You end up with liquid hydrocarbons. So, yeah, that's us your oil. If you didn't find that interesting, seriously, let us know what you think is cool. Just write it down. Okay, so So the oil that formed just like we explained, it actually travels through porous rock until it runs into something called a trap. Think of that as a geological structure that just stops it from moving any further. It starts building up there, and bingo, you've got yourself an oil field. It's kind of fascinating that scientists are still having debates about the exact details of this whole process, and whether oil might form in other ways too, not just from ancient organic bits. People started pulling oil out of the ground way back in ancient times. But the real deal oil boom didn't kick off until the 19th century. That's when the kerosene lamp came along. To actually get your hands on the oil, the absolute first step is figuring out precisely where it's hiding. This phase, geological exploration, is easily one of the toughest and most expensive parts of the entire oil extraction game. Scientists aren't just walking around with shovels, you know? They're using satellite images, magnetometers, seismic waves, and other super high-tech methods. Seismic surveying is actually pretty spectacular to witness. They set off controlled underground explosions in a specific area, or use special vibrating platforms to create waves that travel down through the rock layers. These waves bounce off different layers in the ground and come back up, and sensors pick them up. It's like building a three-dimensional picture of what's underground, essentially letting them see beneath the surface. Once the geologists pinpoint a promising spot, the actual drilling kicks off. A rig, whether it's sitting on land or floating out in the ocean, turns into this giant humming machine that runs non-stop 24/7. The drill string, those are steel pipes with a cutting bit on the end, bores into the earth, spinning at up to 200 rotations per minute. To keep the drill bit cool, carry rock pieces out, and stop the hole from collapsing, they pump in drilling mud. That's a thick mixture, usually water or oil-based. Modern wells can go seriously deep, ranging from 10,000 feet down to 16,000 feet. And sometimes, way deeper, up to 35,000 or even 40,000 feet. For instance, over in places like Texas or Saudi Arabia, they're drilling wells that stretch over 26,000 feet long. And often, a big section of the well goes sideways, horizontally. This lets them tap into a much bigger chunk of the oil reservoir without having to drill a bunch more vertical wells. One of these operations can cost you anywhere from a few $1,000,000 to easily tens of millions of dollars. And honestly, it doesn't always work out successfully. But if the well does turn out to be a producer, oil starts making its way to the surface, either pushed by its own natural pressure or pulled up with pumps. And that's when the next big stage begins, actually getting the oil out, processing it, and shipping it off. Speaking of major producers, Saudi Arabia is right up there as one of the biggest oil producers globally. Just back in February, Saudi Arabia was pumping out nearly 9 million barrels of oil every single day. This country actually has a solid chance to boost its standing in the energy market even further, especially since Saudi Aramco recently announced they found 14 brand new oil and gas fields right there in the country. So, once all the exploration and well drilling is completely finished, the absolutely crucial stage begins, actually pulling that oil out of the ground. If the field is really rich, the oil itself might just start pushing its way up to the surface simply from its own pressure. That's what's traditionally called a gusher. And while it might look pretty dramatic, with those big streams of black liquid shooting up into the air, these days, that method is seen as pretty old school and kind of dangerous. Modern wells are outfitted with sophisticated systems of valves and regulators that allow them to precisely control the pressure and the volume of oil that's flowing out. The oil gets to the surface through a network of pipes, and then it heads over to what's known as a processing facility. That's where they separate it from other stuff that came up with it, like associated gas, water, sand, and whatever else is mixed in. This step often happens right there at the extraction site, either on those big platforms out in the ocean or at bases on land. Separating all those impurities is a pretty cool process to watch. The oil mixed with all the extra stuff goes into this large, sealed tank, and gravity gets to work inside. Gas is light, so it floats up to the top. They collect it through an upper outlet. Water is heavy, so it settles down to the bottom. they drain it off through a lower valve. Oil is in the middle in terms of density, so it hangs out between those two layers. Now, if tiny droplets of water get kind of stuck in the oil, it's not quite as simple to separate them out. That's when they might add something called demulsifiers. These are chemicals that break up that mixture. Or they might heat the oil up a bit, which also helps those different layers split apart. But hey, let's get back to the extraction itself. Sometimes, to increase the pressure down in the rock formation, they use what are called secondary recovery methods. For instance, they might pump water, gas, or even steam into other wells. This helps to kind of push the oil towards the well they're actually producing from. Technologies like this can help them pull out up to 60% of the oil reserves from a field, whereas without them, that number could be cut in half. The average amount of oil a modern well in the United States produces is anywhere from 500 to 1,500 barrels per day. Just think about that for a second. 1 barrel is 42 gallons. Now multiply that by the thousands of wells operating all over the planet. And that really gives you a sense of the true scale of oil extraction. Oil by itself is actually a really complex blend of hundreds of different hydrocarbons, ranging from those lighter gases all the way up to heavy fuel oils. To get gasoline out of it, that's that light, easily ignitable part that internal combustion engines can use effectively. The raw material goes through several technically tricky stages at an oil refinery. It all kicks off with something called fractional distillation. Crude oil is first heated up to temperatures between 660 and 750 degrees Fahrenheit and then fed into a distillation column. This is a tall tower where the temperature gets cooler as you go up. Different components of the oil vaporize and rise to different heights, where they cool down, turn back into liquid, and are collected at various points. The gasoline part, it's one of the lighter ones, is typically collected at levels corresponding to temperatures between 104 and 392 degrees Fahrenheit. But simply distilling the crude oil isn't quite enough to get high-quality gasoline. You only get about 15 or 20% of the gasoline fraction this way, and most of what comes out still has stuff you don't want in it, and an octane number that's just too low. To boost the total amount of gasoline they get, they use a process called cracking. This is basically all about breaking down those long hydrocarbon molecules into shorter ones. The most common way is catalytic cracking, where heavier parts are heated up to almost 1,000 degrees Fahrenheit in the presence of catalysts. This lets them get extra gasoline from those heavier leftovers. Sometimes they also use hydrocracking, which involves hydrogen under high pressure. When it's all said and done, the percentage of gasoline you can get from just 1 ton of oil can reach 40 or 50%. That depends, of course, on the type of oil and how sophisticated the refinery is. The gasoline they get from these cracking steps usually has a low octane number, meaning it would cause knocking or detonate too early in an engine. To fix this, they put it through a process called reforming. This means rearranging the structure of the molecules at high temperatures, usually with platinum catalysts present. This really boosts the octane number, potentially all the way up to 98, making the fuel perfectly suitable for today's cars. In the very last step, they mix additives into the gasoline to improve how it works. This includes things for anti-corrosion, preventing engine knocking, cleaning the engine, and reducing environmental impact. This helps keep the engine healthy, cuts down on harmful stuff coming out of the tailpipe, and makes the fuel more efficient overall. Just one modern oil refinery can process up to 400,000 barrels of oil every single day. That's pretty impressive, especially when you stop and think that daily gasoline consumption in the United States is roughly 370 million gallons. Besides going to our homes, natural gas also gets sent to power plants, factories, and chemical facilities. For big industrial users, they need way higher pressure and volume. They're using pipes with diameters up to 48 inches and pressures up to 1,500 psi. Gas can even be turned into a liquid. They cool it way down and ship it in massive tankers across the oceans. Are you ready to peek into a world where millimeters decide life and gleaming metal travels a path from a piece of raw material to deadly precision? Imagine this. Over 12 billion rounds of ammunition are produced worldwide each year for the military, police, hunters, and athletes. And each one is the result of precision engineering, where temperature, pressure, and shape matter down to the last decimal place. In this video, we'll show you everything. From selecting gunpowder and alloys for the casing, to control tests where the muzzle velocity is almost 300,000 feet per second. Get ready. This isn't just a story about bullets. It's a journey into the heart of modern manufacturing, where technology and science operate at the edge of what's possible. Hundreds of millions of bullets roll off factory assembly lines around the world every year, and each one passes through quality control lines with micron-level precision. The primary material is brass, an alloy of 70% copper and 30% zinc. It's ordered in massive rolls about 0.06 inches thick and weighing up to 6,000 pounds. These rolls are supplied by metallurgical plants, most often in the United States. These are companies like Olin Brass or Chase Brass. The rolls arrive in sealed packaging to prevent oxidation during transport. Upon arrival at the factory, the brass is uncoiled on a special platform and fed into a rolling machine, a huge heated steel drum. The metal's temperature at this stage reaches 600 degrees Fahrenheit to make it more pliable. The brass is flattened. Any deviation means rejection. Next, the brass sheet is fed into a press line, a high-speed stamping press that, with lightning precision, punches out small discs, so-called blanks. Their diameter is approximately 0.75 inches, and their thickness matches the original sheet. The press operates at up to 250 strokes per minute, so every second yields a new batch of blanks. The resulting discs are heated to 800 degrees Fahrenheit. This is necessary for the subsequent deep drawing process. They are dipped in lubricant and fed into a hydraulic press, where, under pressure of up to 100 tons, the disc is formed into a primary casing, still without details, just a cylindrical shape. This process is repeated several times, each time drawing the casing a bit longer and thinner. At this stage, the blank already resembles a casing, but is still far from its final appearance. Each casing is annealed after drawing. This involves heating it to 1,000 degrees Fahrenheit to relieve internal stress in the metal. Otherwise, the casing could crack during firing. Then, it's cooled in water and cleaned in an acid solution to remove scale and lubricant. Next, calibration and weighing. The casings pass through a high-precision laser control system. A weight discrepancy means automatic rejection. Length, wall thickness, cylindricity, and even acoustic response are similarly checked. Special sensors detect if a casing has microcracks or internal defects. Finally, the casing is trimmed to the exact length. A groove for the primer is cut, and the mouth is expanded to accept the bullet in the future. Then it either goes to the final assembly line or is packaged for separate sale. Casings are bought for sport shooting and military orders alike. The next critical stage is primer installation. This is a small but extremely important component that initiates the explosion. The primer is a miniature explosive device. Inside a metal cup is a primary detonator, usually based on lead styphnate or lead-free substitutes. Before installation, primers are checked for sensitivity. Those that react to a weaker impact or have an unstable explosive concentration are rejected. On an automated line, each casing passes through a priming station where, with incredible precision, a mechanism inserts the primer into the rear of the casing and crimps it so it doesn't fall out during recoil. Next, gunpowder. The type depends on the ammunition's purpose. For pistol rounds, most often spherical smokeless powder. For rifle rounds, extruded powder, in the form of small tubes. On average, one .223 Remington round contains about 24 grains of powder. For comparison, a .45 ACP round contains only 5 or 7 grains. Gunpowder is measured automatically to the thousandth of a grain. Too much or too little is a danger to the shooter and the weapon. An error of 1/10 of a grain is unacceptable. Some systems use real-time optical scales that react even to vibrations in the workshop. Once the powder is loaded, it's time to seat the bullet. The bullet itself is another story. Material, shape, mass. Everything depends on the task. hunting, military, sports, defense. But seating occurs with the same precision. The bullet is pressed under pressure into the casing, and then the mouth is crimped so it doesn't pop out during feeding into the barrel. After this, final calibration and visual inspection by eye through a camera with a neural network that manages to analyze each round in less than a second. The rejection rate is less than 0.3% at large enterprises. And only after all stages of inspection, calibration, and final weighing does the bullet reach the final phase: packaging. Packaging isn't just about aesthetics or ease of transport. It's a matter of protection, identification, and logistics. Because when you're shipping 50,000 rounds to a single client, mistakes are not forgiven. It all starts with counting. Bullets are automatically sorted into trays or fed onto weighing lines, where batches are formed in quantities of 20, 50, 100, or 1,000 pieces, depending on the customer's specifications. The cheapest packaging option is plastic trays with shrink wrap. This is a budget solution for the civilian market, convenient for shelves and mass sales. Military supplies are packaged differently, in zinc or steel containers with airtight lids. Inside, liners with anti-corrosion treatment, markings with caliber, lot number, manufacturing date, and QR codes. One such box holds from 1,200 to 1,500 bullets, with a total weight of up to 40 pounds. In some cases, containers with moisture control systems, or even built-in trackers for delivery monitoring. On industrial lines, one shift packages from 100,000 to 300,000 bullets. Some factories operate in 3 shifts, 24/7, especially during periods of high demand such as military contracts, crises, or elections in the United States. The productivity of one packaging machine is up to 12,000 units per hour. In workshops with gunpowder, primers, and explosives, there is anti-static flooring. This is a special coating that diverts electrostatic charge from a person's body or equipment to the ground to prevent sparks that could cause explosions or ignition of explosive substances. Also, the humidity in the workshop is maintained at 40 to 60%, which reduces the risk of dust or particle ignition. In areas with metal dust, oil vapors, and fumes from galvanizing, ventilation with filtration is mandatory. Workers wear special suits made of natural fabrics or anti-static materials. It is forbidden to wear metal objects, watches, jewelry, or phones. Only certified specialists are allowed in the gunpowder or primer areas. Access is strictly biometric. People do not touch gunpowder by hand. Everything is handled through sealed automated systems. Primer formation, explosive mixture dosing, casing sealing, all are maximally automated. Robots or shielded machines handle the most dangerous stages. Powder fire extinguishers, sprinkler systems, and special containers for isolating ignition are placed every 150 feet. Personnel undergo mandatory training every 3 or 6 months. Evacuation, firefighting, first aid. All casings, bullets, and primers undergo visual, weight, and X-ray inspection. Rejects are sent to separate safe zones where they are disposed of or recycled. The factory is guarded like a high-security facility. Video surveillance, armed guards, inventory of every unit. In 1998, in the United States, a plant manufacturing gunpowder for sport ammunition exploded due to violations of storage rules. Several types of mixtures with different properties were stored nearby. The explosion's power was equivalent to several tons of TNT. 4 workers died. The investigation revealed dozens of systemic violations. Therefore, safety at such plants is more important than the product they manufacture.